so prompt. We are super excited to have you all. It's nice to know that we are all willing to continue learning. Let me just say hi to people following online. Hi, Bidogu, SDA Abushako, Abimbola, Adeniran, Adeyemi, hi, Buhari, Chinwe, Christiana, Joseph, Kelvin, Hussein, Taiwo, Sule, Mudipe. Welcome, welcome, welcome. It's exciting to have you all here joining today. I just want you all to know that the training continues, our sessions continue, so that we know this. At least we're going to have, after this session, I'm going to have three more sessions before we call it a close for this course. So, welcome once again to week, this is now week 5, right? Awesome. So, that's week 5, fifth session of this AI Everyday class, and I must say that it's really exciting. So far, how has been our experience? How has been our experience? Good, great. I don't think I've seen. I think I saw a few posts on social media from some of us. It's always nice when you're learning, especially skills that are so internationally recognized like this. That you share your learning experience on social media and tag DSN as well. Let us be part of your story. We'd love to hear from you, really. And let's what's the word now? Amplify your stories, your learning stories. One of the things that touches my heart so much is on Twitter when someone tweets something like, I'm learning this skill and in 6 months I'm going to do something, and then 6 months later the person quotes the tweet and like, guys, it happened. It's beautiful to see that there's a learning curve, and at the end of that curve should come some results. So I want to say big kudos to everybody that has been following this class. Oh wow. So if you missed the last class, that's alright. You can always check the recording of the classroom. So big kudos to everyone that's been following online and offline. Coming here every week is a good seed to sow to your learning. I want to say big kudos to you all. You are all amazing, and we look forward to the amazing impact from these classes. So for people who are already asking for the attendance link online, please, it will be shared with you soon. Please just hold on for a bit. You're going to get it soon. Okay. All right. Okay. So class rules, as we know, our class rules are same. You know the COVID-19 preventive measures is mandatory for physical attendees and people who are not attending physically. If you feel the need to go ahead as well. Okay, participants are required to maintain utmost respect for everyone, and I must say big kudos to you all that we have had no issues here. You are all amazing people. Thank you so very much. In case of a fire, for people here physically, left and right are the fire exits, and attendance at the live sessions is compulsory. So please, you are joining online, you're joining offline, or you are here, you've not signed the attendance at your door, please make sure you do so. And for everyone, I want to believe there is nobody who this is their first class. I want to believe that even if there is, you can still catch up on the sessions. And I want to use this opportunity to actually just tell everyone that all the quiz forms, and they are all there for you, whether you've taken one or not. You can still take it. If you say that, I missed class one, you're not taking a quiz for class one, you can still take that class up until the last session of this class. And in fact, maybe 24 hours one after the last session, because after the last session, we're going to have like a test, right? Don't worry, it's going to be still on your quiz, but it's just cover like everything we've done, and to help people who maybe they had not done maybe some quiz or their quiz scores were low, but now they've learned, so you can take the test, right, to make up for that. So we're going to be doing that as well. Okay, so that would be I just wanted to say that so that we will all be aware. So all resources are there on Google Classroom for you. The classroom will be available even after this class. So we can always continue learning, and we can always continue to find those resources useful. Okay, so we're good on that. Now for people online as well, please, you can scan the QR code or use the link. The link has also been shared to the chat. So please ensure you fill this accurately. And let me say that by tomorrow you're going to see, we're going to release, we're going to public, we're going to make it public the attendance so far and the quiz scores for everyone so that you can see where you stand. All right. But more than just seeing where you stand, the reason we do that is for transparency, and so you can see that okay, I feel this okay, this is recording, and if you have any issues, you can get in touch with us. So that by the time the badges of completion are being given out, everyone that should get one actually gets one. Okay. So as always, make sure you fill this accurately, your email address that you registered with, and even for your assessments as well. Really important. Okay. Nice. So, as we know, we're going to continue this class for 4 more sessions. Previously, I had said 4 more weeks, but now it's 4 more sessions. Why? Because I am excited to announce to you that we will now be meeting twice every week. So, from Tuesday and Wednesday, you can always continue this class. So we have gotten that now that okay, so we are going to continue the class, but it's going to be Tuesdays and Wednesdays. So I kind of like that because there's not too much gap between the days, so that learning just goes back to back to back. All right. So I hope we're excited. I'm looking forward to seeing all of us tomorrow and even more people. Okay. So if you are online, you want to come physically, you are most welcome. You are so welcome. And we look forward to having you as well. And tomorrow we're going to be having a guided class project where we will all be working on some data sets, trying to do some machine learning, and let's see who will have the highest performing model. Okay, so get excited for tomorrow. People following online as well. People following online as well, please. Okay, yeah. People following online, are you not excited? I'm like, I can't even see any feedback from you on the chat. My people, that's better. I think you heard me. My people already responded. So we will have that tomorrow, and then the next 2 sessions are going to be how can we put our models to work, right? Great. So Tuesdays and Wednesdays, everyone. It's going to really be exciting. So technical sessions, you know the requirements, Anaconda or Colab. And as always, like we said, for these sessions, we're using Colab. And of course, you are welcome to use your Jupyter. But please do connect to Colab. The Wi-Fi is available for us to use. The certification criteria stays the same. Assessments complete. At least 3 out of 4 live sessions must be attended. Now, this means that 6 out of 8 live sessions must be attended. Okay? And a verifiable, so it's same time 12 to 2, and a verifiable badge of completion will be awarded to all those who meet the criteria. Alright, so the Wi-Fi password is the same. We can connect the Wi-Fi so that we can get started on today's session. And we're going to start with the review because how well when we get there, and honestly, let me also say that the next conversation we're going to be having like count quizzes and slide quizzes just to test us and have some fun in class. Alright, great. So tomorrow, yes, class continues tomorrow. Tomorrow is our guided project session. We're going to be having like some walkthrough in class, and we'll all be getting our hands dirty on some data set that we provided us. So we're looking forward to that. Alright, so data set is the same we used last week. We are moving on from that. The only difference is the Colab notebook is just AI Colab 2. The difference between the link for last week and this link is the 2. Okay, so you can let me send it to the chat as well. I know it has been sent previously. Let me just do that again. Okay, yes, it's been sent. Nice. Alright, great. So you can use these links to access to Colab. You should have the data. And for people on Google, well, everybody's on Google Classroom. All these details have already been pasted on Google Classroom. Did you get notifications? Yeah, great. So that's so you can for people following online, you can just get it from your Google Classroom. Alright, it's time to go ML. Okay. So I am going to reshare and move straight to Colab. I believe this is Colab notebook. Okay, nice. Right here we go. So we do that, and we are good to go. Alright, so before we get started on reviewing what we did last class, as well as just following up on that. I'm going to just let us review a bit what we explained for last class. Okay, so who can tell us what the difference is between classification and regression? Between classification and regression. Okay, between classification and regression. Let me put it that way. Yes.
The difference between classification and regression is that classification problems are divided into two answers, but they have two possible answers, one or zero, yes or no. More examples could be male or female. Regression deals with problems with continuous variables.
Any other thing? There are a few other things that you may want to add. Anybody else? Okay. One example of a regression problem. Amount of rainfall. One example of a classification problem. Yes. Go on, do it shy. Okay. Any example of classification or regression problem? Give the example and let us see which problem you are referring to. Yes. Determining gender of a user. Yes. Is that classification or is classification? Yes. So classifying based on gender, we can actually look at shopping patterns, look at a few things that are unique to gender, and actually use that to classify as well. Does that make sense? Sorry? Yes? Anybody else? Okay. Who wants to tell us customer trend model? Yes, the customer trend model would also be a classification. Depending on how the problem is structured, there are quite a few things that we can do about that. Okay? Alright, so what about when we talk for classification? We know that we said okay, we know that it's a what discrete variable, right? And for regression, it's what? It's a continuous variable. Yes, those are like so key and so important. We can never forget. Also, what is the key difference between supervised and unsupervised learning? The key difference between supervised and unsupervised learning. Nice. I can see so many beautiful answers on the chat. Awesome. Regression is supervised or unsupervised? Yes. Nice. Alright, what's the key difference between supervised learning and unsupervised learning? Anybody? People online? Yes. Illegal. Beautiful. Legal and illegal. Unsupervised illegal. Beautiful. Thank you, Yemi. Is that what I remember to Michael? Beautiful. Let's see some answers online. More open now. Treat doesn't with Lagos. Yes, correct. Taiwo. Correct. Who goes in? Correct. Nice. Okay. What do we mean when we say a data set is labeled? Because everybody is saying labeled, labeled is not labeled. What do we mean when they say a data set is labeled? What are the labels in a data set? What? Features. Yes. Yeah, but what is it? I would add something else to the output. What if I try to add probabilities to the output? The result. What I'm trying to get. Yeah, so the class or the for I mean, I don't know about it's the class, it's the target, it's what exactly we are trying to predict. Right? So when you see data is labeled, if you are trying to predict if an image is a cat or a dog, the images of the dog will actually be annotated as dog. That is, you can see the machine can find the answer. What it is, yeah. The desired output exactly. It's what we are trying to predict exactly. And for supervised learning, this is going to accompany our data. And the difference is for supervised learning will not have that. So you are left to see what similarities groups in the data set have. Okay? Alright. So let me see if you what are the results there. Nice. So let's get into the session for today. I'm going to do a quick review. Yes, question. Data points. Who wants to give that a shot? Maybe answer that. The difference between the data points and maybe data below. That's a nice explanation. Let me. That's generalized. Okay. When we talk about when we talk about data points, when we talk about the data set is the entire data that you're talking about. Okay? The data set is the entire data. For example, in this example that we have here, the data points, sorry, the data set is the CSV that you read from the URL. That's the data set. That's the whole data. Now, the data set is now what we made into pandas as insurance. Okay? That's the data set. Now, any single attribute, any single, I'll call it technical terms, just simply the intersection of a row and a column. That is, any point where a row and a column intersect, a row and a feature name intersect is a data point. So that means each unique cell is a data point. It's a point in that data set. It's a feature. It's a parameter. But it's not a column. That is the whole row. It's just one. Right? Is it clear? Yeah. So just that intersection of the data points is just a one. And the data point now, depending on how you are using the data point, you are contextualizing the data point. It could also be a row. If you talk about a row of a data point, it could now be maybe a row or a column. Right? But it's just a unit of some intersection in the data set. Alright, good. So we're just going to do a review of all this that we did last week, and from there we're going to continue to today. Last week we covered, I think we covered up to model development, right? We built the classification model, right? And we stopped at evaluating the model. Okay, so let's see how much we remember from the last class. I'm hoping it's a lot. Okay, let's get into it. So, I believe all of us have access and we are on this notebook. Not last class notebook, but the notebook you are on should say classified classification. It's the cell, exactly. So, also to note is let me restart my run time. Okay, also to note is the for those of us working on Coda, at the top right corner, you might see something like copy to drive or changes made are not saved. Yes, so please, so that at the end of the class, all the things you've done are not lost, you might want to copy these to your drive so that you have your own copy and also so that you are able to save your changes. So please, just click on copy to drive at the top left corner, you should see it. Where mine says all changes saved, yours would say something like changes are not saved or something like that. Are you good? Alright, great. So let's get into it. We talked about the different packages or libraries that we need for this. We talked about NumPy, numerical Python for work down, scientific computing, pandas for data wrangling and manipulation, matplotlib and seaborn for visualizations, right? What else? And pandas profiling for EDA. Okay, what's the meaning of EDA? Well, are you sure? Doesn't mean ending discussions always. What's the meaning of EDA? Anyone? Yes? You said the same thing he said. What's the meaning of EDA? They are both correct. It's exploratory data analysis, okay? And it's what we do, like we said, and like we've shown before, what we do to find out before we get to model building. And there's some insight we can use that will actually guide our development of the model. Okay? Alright. Yes, people online actually got it. Yes, good job. I think the first answer came from Ujumwa Edo. Well done. Nice one, everyone. Cool. So we said next up is the URL, and we just said that this is what we need to make sure that everybody access the data set from the shared Google link. And someone in this class can already be thinking of some use cases of this very simple line of code. That is, if you are someone that you work a lot with Google Drive shares and everything, you might be thinking, how can I, if I have a drive link like this, that means I can collect a lot of drive links, and begin to manipulate them and actually do some data analysis without going to Google Drive, taking them one by one. I hope I'm helping someone out. There are amazing things you can do. Don't just limit yourself to, okay, I'm using data science, this is what the code does. The language does the right thing to do. So find how you can apply these things in everyday life. That's what I do. Okay? Alright. So let's look, and we printed the first five. Is what is the YouTube link for? The YouTube link. Okay, the YouTube link is in Google Drive link. Is the link to the data set. The same link that was shared on Google Classroom. And what we're just doing is instead of having us import the data and the different things that can go wrong there, we can simply download the data directly from that Google Drive link. We read it as a CSV file that it is. Okay? I hope the audio is clearer, Joseph. Nice. Okay, so that's for insurance. And so we read the data into insurance, right? And something is happening here. Let me run that cell. I think I missed a few cells I didn't run. Okay, run this. Okay. The audio. Okay. How is the audio now? Let me know. Okay. Now this cell dropping user ID column. What exactly are we doing here? Who wants to tell me? What's going on here? This cell, what's going on there? Drop user ID column. What's that? What's this line of code doing? We're trying to remove the user ID. And why are we removing the user ID? Yeah, but why? Exactly. It's not a predictor really. If we did when we get if we left it and we get we find out that it's not contributing anything to the prediction because we are trying to predict now the user ID is about what? It's a way we anonymize the data set to remove identifying features that could be traced to real people. Because this could be a real data set of people and data ethics dictate that we do not share those kind of sensitive information. So how can we anonymize this data set but still maintain the mapping of because each of these is unique to someone, right? So what we have is unique IDs for each of those people. Now the thing is, so the first question I ask is, does the person's name determine whether the person buys or not? Simple background knowledge will tell us no. So that already means that this contributes nothing. Now, because these are IDs and numbers, sometimes it could be letters and numbers like your DSN AI Plus membership ID. Imagine this, all this is just your DSN membership ID. So we have DSN / AI Plus, right? Am I correct? Okay. If it was in text, right? Easily say that this cannot be in our data set or something. But now it's numbers. If we run this into our data set, the model will try to count the number, but whatever you actually find out from there is totally wrong and actually means nothing to the data set. Okay, get back when I walk about. Oh, okay, it's not relevant. Okay, I think this confirm that now you can hear me properly. All right, great. So let's move on. So that's that line of data. So we drop the user ID and we're left with this. So also at this stage, there are some things, there are some lines or there are some columns that we might already without doing any EDA, you know you don't need them. For example, if this data had serial number, maybe just 1, 2, 3, 4 names, and the index was also in the data set, like this 0, 1, 2, 3 beside it, but it was actually a column in the data set. You can drop it immediately because you already know you don't need that, right? Okay, so that's all about that. Next, what we do is we who wants to tell us what this line of code is doing? Yep. Yeah, it's the only reason we can format like this is because it's already discrete. So who wants to tell us why we are converting life can be mute? Is it? No, it's not mute. It's not mute at all. Okay? Alright. Yeah, so I'm waiting. Someone says, okay, nobody has answered. So why are we converting the purchase to include the target variable? Yes, that's big English to include the target variable. Why are we converting or what are we doing? What are we really doing? Okay, someone else answer, yeah. Go on. Yes. But we can use 2 and 4. We'll still get 2 and 4. We'll still get the same answer. And then 2 and 4. So it's not exactly that. You have the idea, but it's not exactly that. Is anyone online since our model only works with continuous data? Not exactly. So I'm going to give the number for the machine to be able to read. Okay, I'm actually asking this because I want to make a clear distinction between obviously maybe computer can't read it or the model can't read it. Now, we are using text. Okay, you want to answer? The what? The cyclic learning model that we want to use, it does not have the ability, let's say now. Because tomorrow someone can wake up and say, I don't like how the cyclic learning model cannot use text and do it. I mean the kind of community is amazing. So the idea is the model cannot crunch string values, text values, it can only crunch numbers. That's why anything we are using, how many guys up to the model, they saw something like value error, float cannot be, no, string cannot be converted to float, something. You seen it before? How did you solve it? Most times you draw the column or you went back to read your data. You don't see that because somewhere in your data set that you asked the model, it was finding a string and it just does not work with strings. It only works with numbers. So for that model, because we are preparing data to go with that model, because we are preparing data to go with that model, we need to convert every single text to 0 and 1. And you recall, we also did that to gender, this one, right? Alright, so let's move on. So basically, we are using a list comprehension to, okay, this is not list comprehension, this is a lambda function to convert for everywhere in the purchase column that you find purchase, make it 1 and make it 0 if it is not purchased. What I'm saying here is let every value here just be an x and let that value now be 1 if the value before was purchased. Rather, if the value is not purchased, let it be 0. We know there are only two values. So it's either purchased or not purchased. So it's either 1 or 0. Moving on. So we find the let me run all this on so that when we get to okay. So the info method just displays some summary data. Okay, let me sit down and see if that will help. I hope the audio is better now. Okay, so the info method just gives us some summary on the data set, and it's sometimes it can be useful because you can already see here that okay, 14 no objects. I already know that gender is not number when I say object. For another column, they all say no int64. Right? That's just let's just say integers. Now, if I were to see objects in any of these columns where are supposed to be numbers, I know there's a problem coming up. There's one, maybe somebody somewhere entering a data, mistakenly entered some text data. If I leave it, by the time we get to our model, we'll be getting that error, that value error cannot convert, or how does it even begin? So we can do our profile reports, we get our correlation plots, our frequency plots, and all these. We've gone over all these, and the importance is simply ahead of model development, ahead of even because after we build our models, and maybe we might get to that tomorrow, we see that there's something called feature importance. There are quite a number of ways, and we'll discuss that later today. Quite a number of ways to improve your model. But before then, we can already begin to know how can I better wrangle this data? How can I better manipulate this data to produce the results I want? What are the important features there? What are the relationships there? Sometimes these distributions can give you insight to what kind of models to actually use. So that is why we do that. After done with the profile report, very very insightful also is the count plot. So now we are simply counting how many zeros do we have in the purchase column, that is how many people did not buy, and how many ones did we have in the purchase column, and how many people bought. Just looking at this already gives us some insight. We want to give some examples of insights we can draw from looking at this visualization, this simple chart. We can already tell that what majority of those that visited did not actually buy the insurance, right? This is a huge class imbalance. You can see that zeros are more than ones, and by far, and it makes sense because people that are involved in sales, they will tell you that out of 10 people you meet, how many will actually convert into a buyer? So we can see that there's a class imbalance, and that class imbalance actually affects our logistic regression model. And we'll see that as we go on. So we see that there are more zeros than ones. That means for every one, there will be two zeros. Now remember that our machine learning model learns the patterns in the data set. And the machine learning model will be seeing more zeros than ones. Most likely, it could in fact think that zeros could just be the answer and ones are outliers. Do you get? Because we see more zeros than ones. So these are the kind of things we begin to think about, and how can we make allowances for these things, and how can we better build the model to account for all these things. The other plots seem more even male and female seem balanced. Looking at male and female and how they purchase, we can see that for males and females it's almost the same thing, but it seems that females actually bought more than the male. Okay, females purchase more than the males. And then we also did the box plots that showed us the distributions in the data set, how they are distributed and the outlier distributions. That's all. These funny looking plots, that's all they are telling us. Okay, how separated the data is. Now let's move to model building. We've done all this last week, and we are just going to ensure that we are all on the same page so that as we start today, yes, someone who has been attending online can start attending physically. Absolutely. All right. Okay, let's just take a look at this insight that says people that earn higher salaries, right? You can see as numbers increase here, purchase the insurance. While those that earn low salaries, you can see between 80,000 and 40,000. That's where we have lots of the zeros. And of course, it's expected because to purchase medical insurance, most people only think about that when there is enough money. Okay, someone has an error. Did you have an error from so this for profile report? Yes, that's because you did not do this. That is rule theory. So use the code app. You may need to downgrade your pandas and numpy. So just on comment this and run it, restart your runtime. You might have done this, or maybe you did not restart your runtime. So restart your runtime. I had done it before, that's why this is commented, right? And you should be fine. Okay, let us go on. Then we'll go into what we are actually discussing today. All right, so model building, we are importing our metrics, train test split, okay? And the next thing we do is we create variables x and y, and what are we doing in this cell? Okay, who wants to give us some insight? What is going on in this cell? We are dropping purchase from x, from insurance, but we are also putting our purchase in y. Why? Why are we putting purchase column in y, and why are we dropping it from x? Okay, let me call anybody here? No one? Anybody here? Yeah, yeah. Oh, thank you. Separate data sets again.
The x is the independent variable, and the y is the dependent variable. The y is also the target variable.
That's correct. We need to drop the x, the purchase from insurance to create our x, which is the dependent, sorry, the independent variable, right? Your predictors, your features, and the y is the dependent variable that depends on those features, and that's what we are trying to predict. And we said we must do this because why? Why is it actually important that we separate the target variable from the predictor? I think I'll just have to sit down. I really was going to walk, but I just have to sit. Okay, anyone? Why is it important to separate the target variable? What? That's valid. Why was the job exactly given? That's what we are trying to explain. Yes, anyone? Yes. We are trying to find out how the features affect purchase in itself. Yes, but that's not exactly the reason. Why do you think purchase there? There's a particular reason. And it's because yes, you're on the way. And the reason is simply this. We said machine learning models learn patterns in data sets. And if you are trying to learn the patterns that will connect X to Y, that is how Y depends on X. I trying to learn those patterns. If we leave Y in X, we've already shot ourselves in the leg. Because the patterns we are looking for are already in X. And then we are trying to say equals to Y. It's like this. Let me go back up. Let me explain this. the data set itself. And I'm going to explain, I'm going to explain we use it. Okay, let's use this. So we have gender, age, estimated salary, and purchase. We want to find out how purchase depends on estimated salary, age, and gender. So we said let own purchase go into Y, let gender, age, and estimated salary go into X. The reason we have to separate them like this is if we leave what we are, the target variable or our Y, inside the X and go into our model, we are going to show the model the answers to the questions we are asking it. And when we begin to train, the model is training on the answers. And what will happen is we get the model that will most likely like 90 something percent accurate, 95, 99 in fact, or maybe even 100. And you'll be feeling like we've got an amazing model. But no, the model already saw. Because what's happening is every time it iterates, it is going to see, okay, am I correct? But because the relationship, each of these have relationship with the Y. By the time we get to purchase here, and then purchase the Y. What will be the relationship between purchase the X and purchase the Y? You will need more. So every time the model is facing, and because that's how the model was, it will shift itself towards the most correct answer. So, and of course, the model will even most likely discount and say, oh, purchase, and it's not there. Get the correct answer. So, are we actually correct? No. So, your target variable, you cannot train on your target variable. Your target variable goes into your Y. And yes, you are training on it, but as a test. Because the whole of the machine is go through these features and find the relationship between these features and the value in Y. Do these features map the value in Y? You try to find the relationship, then it checks every time. If the correct answer, so it makes its own prediction that whether it's purchase or not purchase. Am I correct? And not only check if it's correct, it checks the value in Y that corresponds to this rule. Right? And if it is purchased, it says okay, I'm correct. It tilts a bit. If it's not purchased, there's some error. And that error, the idea is to reduce the error to the minimum. If purchase is here, once it gets here, it's one, the error will not be minimized. And when we have that model, I don't feel like, oh, this is super hard. I don't think data sets. So it's really important that you separate your targets from your features. Alright. Oh, okay, so a recap is we separate our target variables from the features because we cannot train on our target variables. This means the relationship between the target variable in the X will automatically map to the target variable in Y if that same target variable is in our X. I'm scared. Is it clear? Please ask. Yeah. Mhm. Yes. Mhm. So for like unsupervised, right, they handle the labels. So you don't have to even worry about that. Right? But for supervised, the idea is the reason we have the labels in supervised is to teach the computer what the answer looks like and what the answer is. The computer tries to guess the answer and it needs to know whether it's correct or not. So it checks the correct answer. That's how it keeps getting more accurate. If it is wrong, it makes some adjustments. You remember there was a graph that I don't know if it was myself that showed it or Nikki that was minimizing the loss function when we did logistics. We're trying to fit the model. Every time it iterates, it tries to fit itself better. It calculates that error, the error distance, and it tries to fit better. Right? Okay. So that's how it so it's trying to it does its calculations, it checks the answer. Like you're doing your math. Remember that book in math, you check the answer at the back when you're done. If they are correct, thumbs up. If you are not, what do? You go back and try to solve it. You go back and you try to solve that exactly what the model is doing. So if and what it's doing is it takes X, right? makes a guess on X and just guess the Y. And then it gets its own Y and then checks the correct Y, which is purchase that we sent to Y. Right? And X can be, we can check on something that is what X is not empty, okay? Alright, so X is empty. I think I will explain that when I get back down. So, like I was explaining, the idea is once we have that, now imagine if the Y was now in X. By the time it tries to find the relationship between X and Y, it's trying to find the relationship actually between X, Y, and Y. Because it's trying to find the relationship between Y and Y. Every time it makes a guess, it's going to be correct. Because the answer, the Y is there, the not purchase is there. So it's like we do a class work and okay, wants to give an explanation. Also, prediction and the heads are the features that we use to predict later. So we can't have Y as the feature. We want to predict Y, which is those features after building the model. Sometimes knowing that model, we won't have Y. That's why it's important. That's why we cannot actually include Y to X. We cannot include the label that target. That's what we looking for later on. Okay. All right. So I think is that clear? All right. Imagine it's like what we're trying to predict. We already have it. We don't have it. Okay. Nice. So we drop purchase in X and we put it in our Y. I think that's clear now. So X is actually everything in insurance, everything we have here minus purchase, right? All right. So, hi, what's your name? What's your name? Yes, so is the X not being together now? No, let's get it now, please. Okay, let me drop it and print X. Okay, this is Y, and then let me print X dot head. You see, Y is just purchase. And if I print X dot head, you see that it is everything else except purchase. So what we did was we said insurance from insurance drop purchase. Now because this does not change insurance still has purchase in it. What we are saying is find me insurance and then drop purchase, but then you don't no we didn't put in place true. If I set in place as true here, insurance would have delete purchase column permanently. But we didn't. So we can also come back here and say for the same insurance, just read purchase column and save it into variable Y. Alright. So then we do get dummies for gender, right? Send gender to female and male, and everywhere, and I will explain get dummies like somebody else, but I'm going to run that through again. And the whole idea of get dummies is everywhere that we had, we had gender is just male, female. We want to make these two columns. And how we do that is simple. 0 is male. That means the value of female is 0 and the value for male will be 1. 1 is male. The value for female is 0 and the value for male is 1. It's just that simple. Everywhere everywhere the value is true, it takes 1. Everywhere the value is false, it takes. So the same thing, 2 is female. So male value will be 0 and female value will be 1. 3 is female. Female value will be 1, male value will be 0. Even if we had more categories, we have 4 categories, maybe have been colored or something else, it will create 4 columns, and everywhere that column value is true will be 1, everywhere else will be 0. It's just one, that's why it's one multiple. Alright, so we do that and we save that as our new X. And now we have age, estimated salary, gender female, and gender male. Okay? How do we use get dummy for purchase? Yes, we can actually use get dummy for purchase as well. We actually can, but because we most likely we want our target table to both be in one column, be the same standard series. So KPS, that's the same as one of the column. Yeah, we want it in the same um, row because we want it's just one one series. We're passing one series into one, right? We are not passing multiple. Yeah, we I think so. There's some modules that may be planned. I'm not sure the cycle learn logistic regression model can handle what something like not a series. The series is like a single list, a single array, like one column. Think of it one column. Yes. So think that settles down. And then we split into train and test. We split into train and test and increase the test size to 3% so we can have so that we are training on 70% of the data and we test on 30%. And I think we've also explained why we do train and test, right? Nice. And I even use this explanation to explain the other one. So train and test, and then we build our model. We train our model already. And how do we train our model? We call the logistic regression object from scikit-learn, okay? And we fit it to the data set. That is, we let it learn the patterns in the data set. This is the actual machine learning. This line, this single line is the actual machine learning. Every other thing we are doing is to get this line. I think there's a question like that in the quiz. That got it as and people that missed already got it. So this is the actual machine learning. It's fitting the data set to the logistic regression model. And when we are doing here, and in the actual class, if we wrote this because this is a beginner class and we are not getting deep into the mathematics, we're just going straight to implementation and understanding how it works. If we were to write the mathematics for this line of code, it's not too long, I mean it's logistic regression. So it's just normal some regression and then a sigmoid function. And that's the difference. Why are this question sounding familiar? It sounds like question of the quiz. Okay. Anyway, lucky to well, it's from last week, so this is a new class. So the idea is the logistic regression does that's why it's called logistic regression. It does a normal regression of the values, but at the end it uses a sigmoid function to classify them as either 0 or 1. The sigmoid function that thing that looks like this. So it classifies it, and what happens is everything in a sigmoid function is either 0, is either an upper bound or a lower bound. So either 0 or 1. So whatever value it gets, finds a way to separate it into a clear class of either 0 or 1. That's where the actual classification happens. And that's all this there is. The whole big classification is just a simple mathematical function that is 1 over, I think 1 plus the exponent of the value of your x. And let me see if I can put that. Okay, it's in the other notebook, not here. But that's actually all there is to it. Finding some Exactly, finding some mathematical function that actually maps the results that we want. There's no magic to it. Everything we are doing here, as I want you to do, there's no this super going on in the background. It's just a lot of mathematics. And that's all. Emphasis on the results. Good. All right. So what next do we do? We make our prediction. So yeah, okay, no, we just use 40. I can make this 8. If I make this 8, the value will most likely change. Okay, the other thing is how it shuffles the data. So if I make it 9 and you use 9, you get the same value as I get. But the other thing is just for reproducibility that anybody that takes this, the ones who reproduce my exact result, use this random state, you get it. Because every time we do train test case, it's going to shuffle the data randomly using this value for the random state. So if you want to reproduce the same shuffle, you use the same random state. Also, no, it's just the number. It's just a number, okay? It's just a number. I used to think that too. Honestly, I remember that I was trying to do my do 900, do 10,000. And one day I just noticed that if you do 10,000, it doesn't really affect it. So I now Google actually random states. What does it mean? Yeah, maybe we'll get how we handle the balance. Yeah, there's nothing special preceding it. Models affect our modules. Yes, it will affect our model, maybe like we said earlier, and we're getting to that shortly. So I've changed your say to 9, but because let's just leave at 42 so that other people that might have used 42 will not be saying, I'm getting a different result. Okay, so we explain that and then we use the dot predict function. Our model name is what? Logistic model. We say logistic model, we call dot predict, which is where we now make predictions on X tests, which are X test is just some part of the data set we've kept apart from training. We close the eyes of the model, don't look at this data set. Now we want to test it as if it is working on data it has never seen before. Cool. Is that explanation clear? I know this was explained last week. This is actually just supposed to be a revision. It's getting too deep for a revision for me. Alright, so we make our prediction. Now we get to the most important part, and which is where we're going to really dive in today, which is last question. How come X test Y test? Yes, it's X test Y test. Okay, let me answer Oju or Paul's question. This is important. I don't remember the exact question, but I think I understand what he's trying to say. If you are testing on your X test and your Y test from, and that's why from the code. It's not you won't test on your train because you trained on that. It's have you seen how many of you have seen this meme before? Or someone say, I trained my model and I got 99% accuracy. And it's like, wow, what did you do? And it's like, I tested on train sets. And everybody looks at the person like, because how why would you test on the same thing you used to train? You because the model has seen all the data before. You now tested it on that data that it has seen before. The model will just what is the last one we did? I just give you the answer. But the idea of the test set is a data set has never seen before. Let's really know how to do in real life when it has not seen the data set before, that it has not trained on before. And in real life models, what they actually do, and that's why Google keeps getting better every time. Every time you use your Google Assistant, you will observe you use it very well. You say it keeps getting better. The idea is every new data point to now train on that data again. Right? But before then, you're welcome. I've missed you. And if you train on that data again, just to improve its accuracy, because usually more data means we can find out more patterns, right? Think of it this way: imagine a rainfall prediction model that only covers January to March. If you look at it, it doesn't fall so much, right? But the moment you get more data, you cover January to what? December, you see that it's probably something that looks like this. At some point, the rainfall peaks and then drop. There's a particular rainy season. Now, if you bring it small, in fact, there's some fluctuations in between there. But generally, there's a pattern. But if it's only January to March we might be getting a data set that is just like maybe this part of the curve. So it looks like there's not much rainfall. So usually more data means we can detect more patterns, which means our model will be more accurate. Okay, it's clear now. Nice. Paul gets it now. Good. So confusion matrix. Now, since we know the true label in a test set, we can compare the predictions with it, and hence we can evaluate the logistic model. And here's where we will discover what is really going on in this logistic model. Let's do this one first. Let's see how accurate this model is. Okay? This model says it's 0.6% accurate. That means out of 100, you probably get 60 right. That is quite low. Imagine if this was predicting. Oh, nice. It said this way. Imagine if this was predicting something like cancer, and you go and you say my model is 0. Do you know what that means? That means every time you predict 10 times, 4 of your answers will be wrong. That means you are sending 4 people home with a false positive that they have. You do not want that. So, and for different use cases, we'll get to precision recall, we'll get some other things shortly, but for different use cases, there are different parameters we want to optimize. For something that is not so serious and only occurs maybe once in it's 0.6 super low, but there are sometimes you can say that, okay, this is still okay. Okay, maybe we need more precision, maybe we need more recall. We'll see those shortly. Now, even those 0.6 looks okay, it still doesn't look bad, right? But this is a terrible model actually. And when we get to the confusion matrix, you see why. This whole function is just to plot our confusion matrix, and don't get confused by the name. Honestly, to today, I don't know why they call it confusion matrix. I don't know why. And there's nothing confusing about this video. Tell me, do you know why it's confusion matrix? I don't know why they chose that name. And every time we hear for the first time, they go, there's nothing to be confused about. Yeah, the previous classes are available on the DSN YouTube channel, and you can find them on Google Classroom. So this whole function is just to plot a confusion matrix, and really it can be plotted easier than this. This is the actual line plotting the confusion matrix. This is the confusion matrix in terms of numbers. This is the actual confusion matrix. What we are doing is using a heat map now to make it visual, make it give it color and all that, and then we give it all the label. So this is just a function. I know Nikki explained this last week, so I won't go too much about it. I won't go there. But this way I'm going. I want to stand up to explain because this is beautiful. Now, this tells us our model is before we learn our model are 0.6% accurate. That's 60% accurate, right? Now, what the confusion matrix does, it tells you how many of each of the labels is actually got correct and it got wrong. Now, if you look at this model already, you see that the entire left right side, sorry, for you it's right, right? And for me it's also right. Okay, the blue one, right, is just zeros. That is, there was no prediction there at all. You didn't get any prediction there. Now, here's the funny part. The not purchase, you recall that we say it's an imbalanced data set. You will see that it says truth. This is the actual correct predicted. Let me stand up. I'm going to explain when I explain it for people. I may have issues following online. So the first of all, the general rule of confusion matrix is what you're interested in is this diagonal. And I'm going to explain why, but generally it's this diagonal, this and this are your true positives. That is the true value, what the actual value was, versus the predicted value, what the model predicted. So when it was not purchased 73 times, the model actually predicted not purchased 73 times. Beautiful, right? When it was purchased 47 times, the model predicted not purchased 47 times. That's wrong. But that's what the model did. And you will find that it has no prediction for not purchased that was actually not purchased and then I predicted it. No. No. You didn't even see, you didn't see what purchased at what at all for prediction. It did not predict you get it. It didn't predict it at all. Why? The imbalance in the data set. For logistic regression models, it's a linear model, and because of its linearity and the peculiarity of how it works, it doesn't work well with imbalanced data sets at all. So you might not want to say, 50% accurate, we are okay. But you find out here from looking at confusion matrix that you are not okay at all. This is a terrible model that it is not even give. Let me explain to you. You see, this is the side, right? These are the actual validated tests, and this is what we do. What this means is 73 predictions it made were truly purchased. No, sorry, not purchased, and what did it predict? Not purchased, straight up. 73, nice. Now, it predicted not purchased 47 times, but the actual value was purchased is what? 0. Now, we want to check how many times did it predict purchased and it was purchased? How many times? How many times did it predict purchased and it was not purchased? So, how many times did it predict only purchased? It did not predict purchase at all. Let me give you a true life example of a situation like this that happened to me. So I was trying to predict rainfall, and I had data for like 10 years. And this was when I started machine learning. I remember it because it's one of the funniest things that happened in my life. And If we were to count, now I didn't do my value count. I just went straight to model building. I thought that was all. Just build the model, be happy. And I built the model, and the model I like not was 99% accurate. Because I can do it myself. My guys were trying to help me, my colleagues. I said, "Don't worry, do this." So they knew me and they knew this. They already knew what was going on. I went there and tried that. I think it is 99% accurate. You don't know really. I'm cutting it. The best model in the world. It can predict anything. And let's get people last week. I'm never forget. We just started not the confusion matrix and go back. That was the first time I learned about confusion. What's a confusion matrix? And I went to plot. And I realized my model did not even plot for the days really fell at all. My model doesn't exist there with all the days really fell. And because the data set is so large, do you get it? When you compare the days really fell in 10 years, the days really did not fall. It was actually exactly like 99%. The most like the class balance is like 99%. The days really fell will be like, okay, how many days will really fall in a year? That's noticeable, right? And of course, I think they bound and all that. So the idea was the model was only seeing days rain did not fall. To the as the model rainfall was an outlier, it doesn't even considering it at all. Do you get? So depending on the size and imbalance of the data set, your model could be tricked and it will seem like, oh my goodness, this data is wrong, this data is bad. And like, what do we do? Don't worry, there are ways around this. Okay? Yeah, I think it is when I am standing. Okay, Farouk, I think, yes. So I'm going to explain what I said when I was standing again. I said for the confusion matrix, not purchase, because here on the, let me put on the annotator so that I can. I'm not sure that will be available. No, it's not available. Okay. When we talk about the true, you see that the true side and the predicted side. Yes, that's what we want to witness this to. Okay, so there's the true side and there's the predicted side. I'm explaining this again for everyone, especially for people following online. Every confusion matrix is clear. It's a very useful tool. Sometimes your model will look bad, but when you plot a confusion matrix, you see that it might be okay. Might. So for every time, look at these values. We have 73, we have 47. Now, for every time for the true value, the model predicted 73 not purchased 73 times, and the correct answer was actually not purchased, right? Now, also look at predicted. The model predicted not purchased 47 times, but the correct answer, the true value, was purchased, which is wrong. But when we now come to the predicted purchase side, the model predicted purchase 0 times that it was actually purchased on the true side. That means it did not even predict purchase. On the not purchase end as well, 0 for not purchase. That means the model did not even predict for purchase at all. Why? Because of this class imbalance. Purchase is 1. All it was predicting was 0. So you will find out that it's not actually that the model predicted not purchase. The model just predicted what? Honestly, I feel like if someone actually gets this, maybe we could actually. I just explain something really. The model did not actually predict, it just said 0 for everything. And because 0 is one of your classes, it will fall into a class. Okay? It's the same time on Wednesdays. Okay, I think I'll have to be at the end of the class. Alright, so let's interpret it. There are 52. Is it 52? Okay, now I changed the what do you call it? I changed the values. Now I changed the values that we used to train. The size of the data set. That's why these values are different here. So now we have how many true negatives? True negatives we have 40. No, true negatives are not much is 73. I want to explain true negatives and true positives. That's what we've done. And we have 47 true false negatives there. So what we want are the true positives and the true negatives. A true positive is going to be this lower right, and a true negative is the upper right. That's why I said we are interested in this diagonal. That your true negatives and your true positives. That is when it was negative and it actually got it truly, it got it correctly. And when it was positive, true positive, and it actually got it correctly. We'll give some examples. There's an explanation below, okay? Alright. That is, the true negatives are predicting the customer will not buy and truly the customer did not buy. And your true false negative is predicting the customer will not buy and truly the customer, sorry, false negative, okay. Predicting the customer will not buy and the customer actually bought. That's a false negative. Do you get? That we are predicting the customer did not buy, but the customer actually bought. So it's a false negative. Because our prediction is negative that he did not buy, but we got it false. Alright. Now we got our equation like okay, 0.6% and all that, and we start, oh, this is poor. And if we look here, now this is why the classification reports, I also like doing a classification report. And it already show you that look at the for one, the value is what? Precision 0, recall 0, effort stop 0. So everything is just 0. Support is the number of values, right? I had to do that one. Now, let's look at each of these things again. We have always to check our predictions whether they are right or wrong. There is a true negative, true positive, false negative, and false positive. What we are most interested in are the true negative and the true positive. We are most interested in our true negative and our true positive. Okay? Now, the true negative, like I explained, is when the case was negative and we predict negative. The true value is negative, and what did we predict? Negative. So we got it correctly. The true negative. Do we get that? It's getting confusing. Don't worry, you can't be confused by the confusion matrix. Alright. I now know why. Did you snap picture at the back? Snap picture at the back. Alright. True positive is the case was positive and we predicted positive. That's a true positive. Now it's getting interesting. We talk about false negative. The false negative is the case was positive and we predicted negative. Imagine the case of a cancer patient. See that it's problematic when your model is incorrect and you cannot just deploy any model. So the case was positive, but we predicted a negative. That means the negative was a false one. It was a false negative because the case was positive. And then false positive is the case was negative, but you predicted positive. So you told the person that this case is a positive case, but it's actually a negative case. These things you have to, the logic is just rigid and you have to just get the logic. Okay, I see that people online are following. Okay, nice. Alright, now we saw these other fellows, precision, we call effort score and support. What do they mean? I want to stand up. How people online can hear me. Okay, let me try doing something for people following online. Okay, I want to try doing something so that they can. So people following online, let me know if you can hear me after this. Alright. No, that's gonna be dead. Okay, I was going to mute this and no problem. I'm going to recap once I come back. Okay? For people following online, I'm going to recap once I come back. Alright. Let's see how much I can explain here. We'll talk about precision. Precision talks about what percentage of your predictions were actually correct. So that is your true positive and your true negative. So precision is the ability of the classifier not to label an instance positive that is actually negative. So precision talks about it is a positive class. How good is this model at getting a positive class? Now I told you that there are some times in some use cases you don't care so much. I mean, it's all about the trade-off. For cancer, you want to make sure that, and this is it, you want to make sure that every time you say it is positive, it's actually positive. If you do a negative, that means if you do a false negative, right? No, if you do a false positive, the false positive is not as bad as a false negative. Do you get? If someone doesn't have cancer and you see the person has cancer, the person starts treatment, and maybe later it was good for the person's health. I mean, right? It's not, but I mean, the idea is there's no fatal damage. But someone that has cancer and they tell the person does not have, it can really deteriorate and can be very, very bad. None of them do we want, especially in the health kit. It's very, very, very important. So it's all about getting the right trade-offs. Okay? Alright, so well, the precision, okay. So precision is accuracy of positive predictions. Precision is the accuracy of the positive predictions. Your precision and the formula is simply your true positive, you count it divided by your true positive plus your false positive. Okay, we are looking for the positives. Recall is about what percentage of the positive did we catch, right? And recall is the ability of the classifier to find all positive instances. For each class, it's defined as the ratio of true positives to the sum of true positives and false negatives. Some of these things they just have their connotations and how, for different use cases, you must find what is the proper metric. Usually for classification, the general metric is F1 score. F1 score is like a general, usually when we, and maybe when we do like hackathons, like we'll do a hackathon for AI innovation and for the bootcamp, usually if it's a classification, usually the metric will usually be F1 score. And F1 score is what? It's a weighted harmonic mean, and the whole idea is the best score is 1.0 and the worst is 0.0. So if you see your F1 score is closer to 0 than to 1, comrades, there might be some problem. There is a problem, it's not might. Alright? So F1 scores are lower than accuracy measures as they embed precision and recall into their computation. And that's the idea. That the F1 score is actually looking more beyond just how many did I get correct, how many did I get wrong, to that it was correct. What was the percentage that was correct? When we look at our precision, look at recall. And support is just the number of actual occurrences in the class. Now, we've taken a look at the logistic regression model and we saw that it failed woefully. That's right, it failed woefully. It didn't even predict the purchase class at all. So how can we imagine if it was at work and Leke empowered you all as data analysts last week. And here I am, I'm saying we ask you to do a model for us, and your model is saying nobody is buying. That means this company is going to go bankrupt in a few months. And imagine, based on your model, we decide to close this business. There was a joke, very popular joke I think like 2 years ago. I think some data scientists were making doomsday predictions on some businesses that were wrong, and people were just exaggerating like, because my model has said that your business will close down in 2 weeks, so people should go and find what we do. According to my model, in 2 weeks this business is gone. And it's because different things can factor into different things in these models, and we need to ensure that whatever we are doing, whatever we are predicting per time, whatever we are predicting is the best. That's why you can't just say model just predict and you go home and you're happy and you're smiling. What will separate the people, the data scientists, are those that have understood what the data looks like, the correct metrics to interpret how good the model is, and I've tried to now, okay, how can I make this model better? The first thing we'll try, and usually because like I think they mentioned last week, there's something called no free lunch theory. That is, in actual fact, you should not try one model. Each model is better suited to different tasks. Remember, this model gave us 0.6% accuracy, right? Now let's try another model. We're going to try a random forest classifier. Random forests work as ensembles and they are a kind of decision tree. Decision tree will make a prediction and then find a way to take a tree diagram I'm trying to find the best way to explain this. It will map through some features, and for each feature, it is making a turn, maybe say left or right. It is adding more weight to something, right? And at the end, it kind of like average all that. I know what makes the random forest beautiful is the random forest is a forest of decision trees. It will average the best results for many decision trees, making it really, really, really much better for some kind of data sets, especially in balanced data sets like this. So we go the same in the same way we do our logistic um regression model. Let me get the prediction accuracy score so we can see the accuracy of the random forest model straight up. This paraphrasing. All right. So what is we got? Remember the accuracy of our logistic regression model was what 0.6, right? Let's see what the random forest will give us. The random forest gives us what 0.9. That is a big game changer. See, in model building in development, if your model improves by 0.1, you will have the right to block your street and declare public holiday. But in truth, if your model improves even just a little bit, because think about it, just a little bit of improvement can mean so much to your customers, to the impact that the model will have in its use case. And when you begin to think of millions of data points, 1% increase is what? 100,000. So it's a lot of improvement, even just 0.1%. And now we got how many improvements? About 0.3. From 0.6, we move to 0.9. Okay? Now let's look at the confusion matrix. How good is this model actually? This, my brethren, how good students. He said yours is 0.915 exactly. So you can get different things. It's a good confusion matrix. You can see already most time Africa this is a beautiful confusion matrix. Correct. You can see already that some mistakes that we had before have been taken care of. Before this was zero. And now we can see that we have some sense of balance. First of all, this number don't always have to be the same. It just happens so like that in this data set. Okay? Now let's analyze this confusion matrix. Let me show you. When we talk about the predicted class and the truth class, that is what we predicted and what the actual value is. For not purchase, okay, let's have what is correct and what we want. We predicted not purchase 67 times and it was what? Not purchase. Beautiful. We predicted not purchase 6 times and it was actually purchased. It's not too bad. Very 6. Yeah. We predicted purchase 41 times and it was actually purchased. And we predicted purchase 6 times, but it was actually totally general error is just 4 and our correct is about 108. Talk 208. Are we doing good or bad? We're doing very good. Clap for my model. Clap for my model. Yes. Thank you. So really, and that's how just by switching from one model to another model, we can make so much change in the accuracy or in the precision record or whatever of our model. And like we said, the impact this can have on the actual data set is it's scalable to so many, many. But can you imagine the difference? Now we have imagine the same data set. You know it was 0, 41 misses. That means we could have lost 41 customers. Multiply that by how many thousand customers that this model will run. That means anytime this that model will run on any customer, even if that one model runs for 10 years, it will never predict purchase because it will never get to the purchase class. But this model is telling us, and let's let's plot the classification report and see the precision, the recall, and the others. Alright, so let me do a recap for people following online. This confusion matrix, we said it's already, we can see it is better than the previous one because we can already see that it has a good number of true values and true positives and false, oops, true positives and true negatives. Alright, so this is a recap. For the predicted end and the truth end, for predicted, we predicted not purchased 6 times, but the actual value was purchased. You can see on the bottom left. The top left, we predicted not purchased 67 times, and we were actually correct. The truth value was what? Not purchased. And on the predicted side again, we predicted purchase 41 times, and the actual value was purchase, which is correct. And we predicted purchase 41 times, and the actual value was not purchase, which is wrong. So generally, what you want is you want very high values on the top left and the bottom right. That's why I said this diagonal. No, I remember first time I was just learning this thing. Once I saw that logo, I didn't even care about what the other ones meant. I shall know that this one should be high. This one shall be high. And honestly, that's the idea that this value compared to this value is far greater. This value compared to this value is far greater. And that's why you have this like the bulk for general that these are far greater than these. Okay? Awesome. So I think that we can cover that. And we can now go on that sometimes in actual fact, changing your model might not be all you need to do. You can try 10, 20 models and start to square one. There are so many different ways we can actually improve our machine learning models. Talk about boosting, stacking, feature importance, feature engineering, so many different things depending on the data set and different techniques really. So, but in today's class, we'll cover one technique which is hyperparameter tuning. You see that we've been declaring our models really simply. We just say the linear regression, we put the bracket, but there are some features that make up that linear regression. There are some hyperparameters in that linear regression that can be tuned for better results. Now they are usually okay, let me plot this one accuracy again. That's 0.9, which is beautiful. Let's take a look at the classification report. You can see this is a much better classification report. You can look at it, you see that for 0 we have high precision, high recall, and high F1 score. For 1, although it is lower than 0, but remember the 1 class is highly what? Imbalanced. The 1 class is highly imbalanced. So for this to still get a 7, it's still kind of okay. So we can say 0.87 precision recall, and then our final calculation is 0.9. Now, can we make this model better by tuning the hyperparameters? Probably, yes. Yeah, the confusion matrix is for us to know exactly how the model is performing on each feature of on each label of your classification class. Because like we said earlier, you can get a model like this that will be 99% accurate. If I can take this data set now and imbalance it greatly. If I imbalance the data set greatly to maybe about 90 to 1, this model, the logistic regression model, will give us 90% accuracy. But does that mean it's actually 90% accurate? No, it's just highly imbalanced. So you can see, we can actually tell exactly how the model is performing on each label class. Alright. So that is for on that. Now we want to look at hyperparameter tuning. Now, for example, we actually can tell the number of estimators, that is trees, or sorry, forests that should be the random forest model. Let me put the accuracy just on that. It's like every time we run prediction, we can be checking the accuracy and see how well we did. Okay. Alright. Now, one of the simplest of them is the estimators for random forest. And we can just keep changing the estimators until we get a good value. But there's a problem as well. Remember overfitting and underfitting. We can build a model that will be 99% accurate, and when we bring new data, the model becomes 2% accurate. And you're like, what's going on? The model didn't learn the patterns in the data set, it simply memorized the patterns. So for that particular data set, the model is beautiful. But once new data comes in, it doesn't know what to do. And on their fitting, the model didn't learn the pattern well enough. So maybe the pattern goes like this. The model stopped here. So if your data falls here, the model will be, yeah, we're good, we are good. But by the time your data falls here where it didn't learn, there's a problem. So we need to be able to say, all right, how can we get the best model? Now we're just going to do the simplest, right? And then we'll look at another slightly advanced technique, which is really more accurate, right? And we'll talk about the elder brother of that technique, which is even more accurate. And you will learn why. Have you seen this meme before? Machine learning, they say machine learning engineers. Why are you playing around in the office? And the guy says, my model is training. There's nothing you do. Or since morning, we've been training model now. Did we have to wait? We'll wait this afternoon. So let's take a look at this. We increase the estimators to 50. I think by default, is it 100? Am I correct? Before, let me check. You can actually check if it does over in what's it? Google Colab. Let me just go over here. Yeah, N estimators is by default 100. You can see here, you can see these are all, see, take a look at this. These are all the hyperparameters you can train your model with. And by tuning some of these hyperparameters, you are actually able to improve the performance of the model. Look at all the parameters you have to play with. But let me warn you, and when we get to what we are going, you will see. The more of these you try to do, the longer the time exponentially will take. I just remember computational accommodation. Yes. A lot of our it should actually be, but it's one of the basis of this of machine learning. And other probability theory, especially. The idea is for all these guys, all the estimators, premium mass, their samples, especially that is their values or field values, you can give it a range and say, keep testing this range for the best value. And by the time you will be trying to find between 5,000 to 10,000 videos and then find the best one for you. So that's really and that's why it's funny how when we get to things like maybe we need a multi-layer perception for second and your model is imagine if your model normally would take 10 minutes to train. Our model will take every second to train. Let's say second. But they have to tell you because this is another place. We can do a and a bigger data set and you so but if you really and you try to maybe a grid search on it, that's 10 minutes times so thousands and because I mean we don't search for my colleagues here, the machine engineers like Jeremiah and Tejimola and Orolua, they can tell you that they train model for days. Some of them are trained model for 17 days, for 17 hours. The model was just training. It was just training. Now people like to brag on how long their model took to train. I remember doing hackathons then. The what everyone wanted was don't close my laptop, don't close my laptop. I've been training that model for 4 days. I'm not kidding. People because the idea was the longer your model took to train, the better your model will be. But that is not always true. So how can we check? Let's take a look at this now. We did 50 estimators. What's the accuracy? 0.908. Let's make this 150. Let's see. We cannot keep randomly changing like this. This is even lesser. Let's try 200. We can actually keep changing randomly like this and not be checking the accuracy and the confusion matrix as well. Let me try 2000. You can see that it's taking longer to do now. When we got to 2000, 2000 sync is actually an overkill. I won't be surprised if it's just 0.9. It's just going to like now this already tells me something that this data set might not be able to fit this model beyond a 0.9 range. Let me put it back to something sensible. Let's just put it on 150. Right? So now by this little that I have done, I can already have an insight that this model might not be able to improve on this particular random forest a little more than this. Paul, I see you. Okay. Right? So confusion matrix, for that you can see we have it's still roughly the same thing. Okay? Why is it 0.925? That's a different split. I think I used a smaller split before. So we can try something. Let's try something. Let's try increasing the data size. Who has an idea of how we can increase the size of the data? Change the test size. If we change the test size, so that you get. So let's change our test size to 0.2 and see what effect that will have as well. 2 hours. For 17 hours, the model was just training. Just training. Let's look at this accuracy. What do we get? So it's still 0.9. But you can see something different. So we'll notice something different. We have lesser false this is a false word. No. We have lesser false negatives here. But this one also reduced a little. This one was 6 before, right? Yeah. So actually it improved, but just slightly, almost imperceptible. Now, this is not advised. Where is it? This is not advised, but I won't lie, something I've done before. What men will go to look for accurate models, and what our amazing female engineers will also go through sometimes, it can be a harrowing task. And like a friend will say, sometimes it's just trial and error, honestly. So what do we get to 0.1 test size? Just a bit to increase the data. Someone that knows what you really say, but I know what some of you already do. I'm sure someone in this class has done it already. Am I lying? Who has done it? You have done it before. Raise your hand. Not for my hand. Or you even went lower. So it's all just in a bit too, but this is not advice because you now have so small a test size that can not going to show you what your model is really doing. Alright, so let's leave it at 0.2 and go on. Alright, so that's for the random forest there. Alright, so making the model better. Alright, okay. So now we will look at something called the random search. There are two search optimization algorithms. One is the grid search and the second is the random search. I chose to use the random search in this class basically because of time. And the difference is this. The random search, you get all those parameters I showed you earlier, the hyperparameters. Whatever you define for it. Random search will find the possible combinations of all of them and randomly just select a range. Randomly just select a range. When you say grid search will search through every single possible combination, which is why grid search takes a longer time, but usually gives a better result. But when time becomes important, random search will give a better result faster. You can only grid search because most people take the training model for 5 days. That's what happens to some of them. You can only grid search for days. But a random search, depending on you, 1 hour, but in this class, you can't do that for 1 hour. And this is a small data set, exactly. So what can we do? In about 2-3 minutes we'll be done, don't worry. So first of all, we print the parameters. Let's look at the parameters currently in use in our model. We have the bootstrap and all this. You recall I showed you this when the let me see if I can find it from this object. No. I'll have to go to maybe what all these are the things we show. You can see your n estimators as 150, right? From here. When we set it as 150, right? Okay, now we will import the randomized search, and what it does is simple. We declare the number of estimators. This can be a list, but I'm using the numpy namespace to create 10 numbers between 20 and 250 that are spaced evenly. So it will space them evenly. So Kemi, you were asking how we can make a model better. I hope you are seeing some of them already. But I can already tell from what we've done already, I can already tell because it's random forest we are still using. You most likely, and what I've done before this class, most likely will get maybe the same result of, because this model cannot really improve so much more than this. Okay? So the number of features to consider at each split. So basically what we are doing is we are putting options for each of these guys. For each of these hyperparameters, we are setting some options. That's all randomized search is doing. And for each of them, randomized search is going to create a model and check finally what the best of them will be. So let's see what we have. These are the parameters for randomized search. We have this number of estimators we are testing. But remember, we've tested up to 2000 before. And we saw that it's still almost the same thing as 200 and 150. So all these ones already know that when let's check them out. Max features, auto and square roots, max depth, depth of the tree, minimum sample space, minimum sample leaf, bootstrap. Bootstrap is without replacement or with replacement. Okay? And then we initialize and we train. That's all that's happening here. And we can set the number of iterations. Right now, let me increase it. Right now, we have what we have here, which is this, but this can change. This can become where is it? Okay, so the parameter distributions are the random grid for the randomized stack. That is this that we created. Okay, n estimators is n estimators. This okay, and these are the values that have been printed. Now, the iterations is how many times this randomized search is going to try to find those proper values for each of those models. I can make this maybe for combination, sorry, make it 100, but it's the more the iterations, the longer it's going to take. Let's start with 50 and let's see how long 50 will take. We cannot begin to change values. Okay? Alright, I think I dropped an article, I dropped a few articles on the classroom that explain each of these things in detail. So you want to get down into the root of everything we're detail, please check out the classroom and make sure you check out that article. Now we fit it and the training begins. And honestly, there's nothing we can do but wait. There's really nothing we can do but wait. Now imagine if this thing was running for 3 hours. A funny part, imagine if it's running for 3 hours and you've used the wrong data set. I'm telling you things that happened to people before. Or you've made some mistake. So we are done. Not so long. Let's try 150. Okay, hopefully this will finish before the class ends. But this is an idea. So what it's trying right now is fitting infos for each of the 150 candidates. That's 150 combinations of, no, not combination, 150 parameters that have been declared total for 450 fits. That's about 450 models, right? So it's training. Someone is asking for the attendance link. So it just keeps training and just keeps training and it just keeps training. And it's going to keep training like this until, like, if it doesn't finish, it doesn't finish. And this is even shorter. Like, remember we said to try what? Randomly. For all the possible combinations of all these things, it will just pick at random over some ranges. Just pick at random. Now, the number of random it will pick also increase, right? But basically, it's just picking at random. But for the grid search, it's done. For the grid search will check every single one. Because there's one thing that can happen with a randomized search is you find a local maximum, or for a loss minimization, let's say local minimum. That is, at some point, it looks as if it's the lowest loss. But if you actually continue training, there might be a lower loss again. So there are sets of maybe this is a lower loss, and there is in the entire training set you have, there's a particular lowest point of loss, which will be your global minima in that case. So let's see what are the best parameters that we're able to get. So bootstrap has true, max depth 15, samples leaf auto, minimum samples leaf 42, minimum samples leaf 2, and estimator was 173. So that means estimator 173 actually works better than 150 according to our random search. So these are the best parameters to be able to give us. You have a question? It depends on the values you use. Did you use random state as 7? No, exactly. So we won't get the same. You see, someone got a different answer. We won't get the same result because of the different random states. And maybe I think I changed my data split percentage as well. Alright, so these are my best parameters. Now I don't need to memorize the parameters or type it out. All I need to do is to use this call RF random the best parameters. That's all. So let's compare this with the former model that we built. Let's compare this with just a normal baseline random forest classifier model. We have random state at 7, right? It's either we do this, but this will be almost random, or we just leave the random state at 7 so everyone can get the same answer. So we call it a baseline model. We fit this model on our train and test, we get predictions from it, and we find the accuracy of that. That's our base model. Then we do the same randomized search that we done to get these best parameters, and we do this again, try to fit it and predict and find the accuracy. So let's see what the improvements will be. Let's see what we're going to get. You can see it's still what? It's still largely the same thing. Actually, it's still largely the same thing. And me, I'm not even surprised. It's very much possible that's why you notice that at first I was trying different estimators to see, and you said it was capped at 0.9. So there are two reasons we can begin to suspect for this. First of this is a very, very what? Small data set. That means it was even worse off. So it's possible. Do you get? It's actually possible that you get something worse off. But you know it's a randomized search. And we just did the baseline. And what it's trying to do is from all the features you've given, it's random selections. It could not find a better one. If we run it again, we get something even better. Okay? So sometimes this happens. First of this, and what we begin to think of is, can I get more data? Can I get maybe try grid search? Can I try another model? There are so many classification models out there. I mean, so many. And we've only touched 2 in this class. So tomorrow, I want you to come excited. I want you to really, oh, you came late. So classes continue every Tuesday and Wednesday now. So every Tuesday and Wednesday classes continue. Okay? Alright, so tomorrow what we're going to do is we are going to run through some of these things again, but in a different way. It will be like an in-class exercise. We will throw you the data sets and you will build your own models, and we'll see who will have the model with the highest prediction. Do you want to try that? So ahead of tomorrow's class, you might want to review what we've done, check out some things, do some things, and if you are someone that you might want to go and quickly Google top machine learning models a beginner should know. I'm already giving you tips. And that's how you Google it now. Top, and actually I shared some of it on the classroom already. So just check the classroom. For people online too, you are expected to participate and want to see your models. In a Google form. Everybody will actually submit in a form like their best models. We'll show you how you can submit tomorrow. So I'm glad that we are going to put this class to a stop here for today, and I would like to take a few questions. So questions, people. Okay, I saw his hand first. Yeah. How do we so I saw a question online. Online, someone is asking, how do we know a good model? A good model is simple. Your metrics, the classic depending on your model is your metrics. Classification metrics are these. Regression metrics are different, you remember? And your classification, your sorry, it's what's called your confusion matrix. Okay? your confusion matrix as we explained, and your classification report. Yeah, your question. I didn't work it.
Hi, okay. I wonder what this all means. I wonder if this means that if we gave a random data set or data point to our, I guess, algorithm, that means it'll be able to tell us if that data set or that data point will, if the individual that is attached to the data point will purchase or not purchase.
Exactly. So what this all means is when this model is deployed, as we'll see from the last two classes, when we deploy the model, what we supply to the model is what was in our X. When we supply purchase, because we don't have purchase, we don't know yet, right? So what we have is our X, right? That's what we are supplying to it. And every time we supply that to this model, recall all we need to do is model dot predict. Every time we supply that, the model will now tell us whether it's correct, whether it's purchased or not purchased. But what happens now is we already know from what we've done is our model is 0.9 something percent accurate. That is, if I run this 10 times, I'll get 9 correct answers. Something like that. But then classification metrics and your the computer metric will tell you that it's not just about being correct, but when were you wrong and when were you actually correct and what is incorrect. So yeah, it's this thing that but a good confusion matrix will have where we have 5 and 3, a perfect model will have 0 there. But like someone told me once, and I have seen, and you would learn very soon. Getting a model that is 100% accurate is nearly impossible. Nearly impossible. It's, unless there is an exact mathematical function that maps every feature to the y variable, and you have a large data set of that, you will get 99 point something percent accuracy. Because if we do it here and we find maybe area of the square, you can do that yourself. Try it out. Create an Excel. Okay, you can do the number, but create an Excel and do length, put the breadth, and let the y be the area. And try to do a linear regression on it in Python. Use it in Python. Try to do a linear regression. Let it be very long. Do a random. Now you can do random values in Excel, right? Let it be like 5,000 values. And try to do a logistic regression model on it. Most likely you will get 99.999 something percent accuracy. You won't even get 100% accuracy. I tell you, it's really amazing. And you might get 100% accuracy too. These things sometimes you just have to try it. So please let's go and try some of these things. Let me see more questions online. I think I see a few questions online. I can answer. Okay. How do I access this data set? How can we deal with missing? Yeah, missing data. df.fillNA will sort that for you. Don't worry, tomorrow's data set might not have missing data, but you can easily just Google that. I tell you, it's really, really visible. Stella, you can access this data set on the Google Classroom. It's there from the last class. Just check the last class. All right. Thank you, Benjamin, for answering that question. Of course. Yeah. By the time we get to the, I think towards the end, we'll do something about dealing with missing data. Okay, so she's asking where we are getting the data points from putting the model from. So it's the same data. We are now trying to maybe if we change the model will fit the data better. That's all hyperparameter change is doing. Because each of these models can actually be visualized. Logistic regression looks like this: sigmoid, the activation function, right? And is there a way? So the idea is there a way I can turn that if I turn that graph a little like this, maybe the fit data points better. That's all we're trying to do hyperparameter. And each of those things we are changing controls some parts of that. So if I change this part, how much will it improve this part? We're not adding new data. Same data. Just column will not reduce our data. It will reduce your features, but not your data. Between SVM and which is generally faster. So it depends on your data set. It depends on your data size. So I'll give us an assignment. Go and try the SVM out on this. Use a Python time module to time it. Right? So when it's done, you print out the time duration. You can do a simple time before minus time after. You can also get a time duration function, I think. So yeah, you can try that out. That's one way. Okay. So, in the absence of no other question, I'd like to say a big thank you to. Okay, one more question. All right. Big thank you to everyone for making this class. Looking forward to tomorrow's class. Come with your typing hands tomorrow. Come with your what I call it, your data shoes and your data gloves, and let's deal with some data sets. Yes.
What exactly does random forest mean? What is the meaning behind it? And also, why is random forest prediction accuracy was much more better than the logistic regression accuracy? And also, does the random forest does it fall under supervised or unsupervised? Does it have its own?
I'll ask you the last question. I'll turn it back to you. What's the answer? Look at the data set we just used it on. What's the answer? Hmm? Yeah, and what type of classification is that? Supervised or unsupervised? Exactly. You answered the last question yourself. So, for the other questions, yes, the random there's a like I explained, the random forest is a forest of decision trees, which is what makes it really amazing. First of all, trees use boosting, bagging. Trees are a bagging technique, and when you now bag trees into a random forest, it just usually mostly improves the accuracy. Now we can go into more details, but what we've done is I have actually shared when you ask the exact articles on the Google Classroom. Have you seen them? And two videos, two short videos. I checked a lot of videos and found two videos that will suit and really explain these concepts to you. So please go ahead and check them. But basically, random forest is a collection of decision trees, and a decision tree is a mapping going through each of the features. If this is this, what would this be? And trying to create nodes for each of these decisions, and each node leads to a different node based on the decision taking. So if this is true, it's my branch this way. Or if it's false, my branch. If this is false and this one is true, it's create another branch until the final answer is actually gotten. And we now take that tree and create a forest of them, like many of those trees, right? So create your random forest. So that's an oversimplification, really. But please check out the video. And yeah, there are two videos. Please do check them out. I think to support us to check them out, maybe we'll also place the videos. Um, okay, maybe we might not, but let's see how it goes. Okay? Alright. So thank you all. There's no best, that's the thing, there's no best outcome really. There is, I can tell you that for a fact. There is no, it depends on your data, it depends on so many things. So you have to try them all. And rather than trying them all, someone that is very good with EDA, that's where EDA comes in. You can look from EDA and already begin to know that okay, this model will better suit this data. There are actually something, for example, logistic regression, one of the assumptions it makes is that the model has, if I remember correctly, has its unimodal, that it is a normal distribution, if I remember correctly. That means if I take a data set that is not that does not follow that distribution to a linear to a logistic regression model, most likely the model will not fit it very well. I'm not sure if I'm correct with that assumption. I think it is correct. It's not fit well. So these kind of things are the things you actually look at for your model selection. Now we'll talk about okay, the next class is that's I think when we are deploying our model, we'll look at a few of those things. Yeah, everybody will deploy. Take care has empowered all of it last class. You're all data analysts. One update it on your LinkedIn. Don't update it on your LinkedIn, no, so that they call you for interview and you will not be. But at the end of this session, yes, and when you have, if you do complete this session, you get a badge. I'm very sure you can stand out there and you can actually, you can do a few things. Um, Yes, so this is simplified workflow. Don't worry, tomorrow you have access to all these notebooks. Do as you wish. Don't worry. Okay? Yes. Yes. Good question. Most likely. Most likely. Most likely. Because of the way it works. It's going to take what basically when you have imbalanced data set, there are usually about two ways to do it. There are generally two ways to do it. No, three ways to do it imbalanced data set. Find a very robust model where that you can begin to talk about class weights. I actually tried class weights with the logistic equation, it didn't improve. You can do class weights, or you do what we call oversampling or downsampling. Oversampling is the class that is very small. There's a way you can increase that class. And downsampling is a class that is very much, bring it down. There are ways you can generate synthetic data. You can look at the most popular that I know, Anderson and Smooth. You can check those out. Those would work as well. Yeah, there's a lot of things. Yeah. If we be, don't let me scare anybody, please. Don't worry. So please, it's we keep it simple. As long as you follow, you check through the. Okay, somebody is asking again. Can we get the record before tomorrow's class? Yes, the recording is already on YouTube. We'll share on the classroom immediately after the class. You only want the code on the same copy. Both are the same thing, Rosemary. In a situation where you're trying to submit the code and you're getting error at the length of the label, okay, if you're getting data on the error on the length of your label data, it most likely means after you make changes to your data set after you split it. Or maybe before you split it, there was you made some error in your splitting. But it's easily there's no error that you create that cannot be solved. And somebody has had that error before, so you can also check it out with Google. So thank you all for today's class. I think you had a question. Okay. The one you said no now is scary. The one you said no is like no, no. Please, it's okay. All right. So, in absence of another question, thank you all for joining today's session. I'm looking forward to tomorrow with you all. It's going to be exciting, really. It's going to be really exciting. I know you can ask questions, ask your mates, what are you doing? How is your model doing? How is your model doing? How is your I use LPMO, no, I use status, no, I use the LGPM, I use text tables. So many other things you can try. Alright, so as always, my colleagues at the back need you for video interviews. And I will also be there for those interviews. So if you want to get interviewed, please do see them at the back. I think we have a special room today, right? Yes. So I'll reach out to some of those personally that I would like you to actually do the interviews. So I'll just walk around and see if you can do that for us. So thank you all for joining this class. Someone asked for the attendance. Okay. After the class, that may be weird. Okay. So thank you all. We'll see you tomorrow. Cheers, everyone, and bye bye.